Hey guys, we are group 125 and this is our update 2 for our image upscaling neural networks project. So as discussed before, image upscaling is a very important topic nowadays for like medical imaging, security, digital entertainment like games and movies, etc. So this project basically tries to use neural network models to upscale images, two kinds of models. One is a CNN and one is a transformer. So what we did was we used a diff2k data set and we downsampled the images using bilinear interpolation by 4 times. So this gave us both the low res and high res images as our training set. So as you can see, this is the low res image and this is the high res image. Low res is exactly 1/4 of the resolution of the high res image. So we need to understand how the input and outputs are produced. So the inputs are, as mentioned, low resolution images and the outputs are enhanced images. And we're using two things, that is peak signal to noise ratio and structural similarity index measure, to determine the quality of the output. So since there were only 800 images available, we had to do data augmentation. So we cropped into images and used those as high-res images, and correspondingly used bilinear interpolation to create low-res of those images. The images were cropped, rotated, phase shifted, and all of those things. The model training happened with the two models, right? CNN and transformer. We had the training pairs and we also had a loss function, which was the MAE for the PSNR. And yeah, so the model architecture for the CNN model was 16 residual blocks, each one containing 3x3 Con2D layers and a skip connection to the output, so that we can preserve some information about the structure of the image to the output. We do upsampling via depth to space. So we have a custom upsampling block, which is a Con2D layer that expands the channels as an intermediary layer. And we do a final reconstruction using the skip connection and the upsample layers to get the final image. So the transformer based models does slight modifications. So we replace the CNN blocks with the transformer attention blocks. We use multi-head self-attention to map relationship between pixels using positional encoding. And the patch embedding also covers spatial image features. So this also, we go patch by patch and we create tokens for each patch. So we do similarly we do pixel shuffle upsampling, which is depth to space, and we also again use skip connections here also to preserve some spatial information throughout the network. So as you can see, these are the results. This is the low res image, this is the CNN output, this is the transformer output. The transformer, from what we observed, more or less is always either equivalent or better than the CNN. And the data which we and the training time for the transformer was half the time for the CNN, and the number of parameters was half of the CNN. So we feel the transformer is the better model here. So this is the training graph where we can see that the loss kept going down. The loss decreasing suggests that we can still train more. Even though the model is learning, but the PSNR, if you can see, the PSNR is not going down. That means the model is still learning but is producing blurry images. So there are instances where the validation set the model performs better than the training set. So next steps of improvements is probably increasing model capacity. We can adjust decay ratio to stabilize the PSNR improvement, use a different loss function, and try to get more training data. That's it, guys. Thank you.